Now I'm totally lost.
Yeah. So please, you can. Yeah. No. I mean, you feel free to input. I'm just recording the stuff.
Good morning. My name is Jan van die Venter, and we have the privilege of having Paulo Pinheiro present his research. He was yesterday the external reviewer for licentiate seminar, and today we get to talk about knowledge graph-enabled scientific data repositories.
All right. Thank you, everybody. Thank you for having me here. It's an honor for me to be invited to this select group of people and to be talking about the work we have been doing during the last, I would say, specifically in terms of data repository, the last 15 years. This has been a long journey to reach this point. And in the process of getting here, for instance, I was there in the US developing, along with a very large group of people, part of the standards of the semantic web. So we were involved. The person who created RDF is actually a former colleague of mine. He was in my office for 4 years. And then we joined the DARPA demo project. And that was an initiative of DARPA, the same agency that created the internet. And they were very excited about getting the web that was kind of brand new at that time and make it. The whole motivation was to make the web useful for a machine like it is for a human. That's the whole idea of the semantic web. And the basic idea is that as we can go, I don't know if anyone here speaks Chinese, but I don't. And I can go to a website that is in Chinese and I can read it. The only problem is that I cannot understand it. So, and if I were a machine, that's how the entire web would be for me. I could have access to it as a machine. I could go to the places, I could read them, but I could not understand anything. What's the problem of machine not being able to understand anything? The problem that I like to mention is that machines are very good to do very repetitive tasks. But if they are very large tasks, they are very good in doing it. So if you go and give a human a task of ordering 5, 10 numbers, a human will be able to do it even just glancing at the numbers. But if you give the same person, the same human, 10 million numbers, that person is going to struggle a lot. And so this is the vision. The vision is that we have the machines. The machines are good doing tasks for us, but they could not do anything on the web and using the content that was in the web. And this, I'm talking about 2004, around 2004. Since then, we developed several things. We engaged many scientific communities. I was a program manager for NASA, for instance, for 8 years. We developed part of the Cassini project that went to Saturn. We participated in the SOHO project, that is the space observatory looking at the sun. And when we are doing those initiatives, you clearly see that you need to have something more cutting edge to manage those projects. Anyway, let me go inside of the talk itself here. So this is work that has been done right here. I'm the first out of this presentation. Actually, this was presented in a conference 2 months ago. Enrique is is at RPI in New York. James Masters is a member is a manager for Mount Sinai School of Medicine in New York City. Matthew Johnson works for the U.S. Air Force. And he basically works for the group that work with information management and knowledge management for the Air Force. Jeanette Stingone is an epidemiologist at Columbia University, also New York. Sofia Bego is from Mount Sinai as well. Marcelo Bach is from a university in Brazil. And Deborah McGuinness, she is my main co-author during the last 25 years, and she's also from RPI. So actually, it's nice to mention Deborah McGuinness here because one of the topics we're going to have here is to talk about ontologies. And Deborah McGuinness is one of the leaders in this area of ontology management, and she has, for instance, a paper with 9,000 citations called Ontology Development 101. And the reason I mention this is because what is one of the key points of this presentation today is to show what's the next step. Because during many, many years, we have been reaching out for many scientific communities and asking them, look, if you want to share your knowledge with other people, you need to formalize this knowledge. So, for instance, this notion of ontology is not new. It's something that has been around for centuries, especially in the scientific, in philosophy and logic. They work a lot with ontologies. But what has happened during the last 25 years is that we have this new notion of ontology that is a computer science-based definition of ontology. And that's not exactly the same thing of the traditional notion of ontology that we have in the past. One interesting thing is, what is an ontology? An ontology can be any document that would provide you a vocabulary to describe a universe of discourse. Okay? And that can be just a list of terms. That's already an ontology. If that list of terms is organized as a taxonomy, even better. If it's a taxonomy with restraints on top of it, with a syntax to describe the terms, even better. So you can go on and range from a very simple ontology to a very complex ontology. It's not correct to say that, for instance, if it's not fully formalized, it's not an ontology. Okay, and what has happened during the last 15 years is that we have engaged many scientific communities to develop their ontologies. And to this, what I mean by this developing their ontologies, I mean it's something actually very nice to actually see BioPortal. If you have never seen BioPortal, let me go here and share BioPortal right now. BioPortal. That's the initiative from NCBO. That is it's a program within NIH. And inside of this website, you can find an ontology. And I actually going to just pick one ontology that we're going to be using today. For instance, I use this. I use a lot this ontology here from Michel de Montier. That is the style ontology. By the way, this is the same guy who wrote the paper about the FAIR. FAIR finding, making data files findable, accessible, interoperable, and reusable. That's actually a part of the initiative of the European Union. And now it's a part of the law requiring every data collected using public funds to be findable, accessible, interoperable, and reusable. That's called FIRE. And Michel de Moitier is the same guy who created this ontology. That's just an aside note. But anyway, if you go inside of the ontology, you're going to see that you have a hierarchy of terms. You actually start with very high-level terms here, attributes, objects, and so on and so on. This is very large ontology. But what's the point of mentioning psi? The point is that we have managed to get lots of scientists to build ontologies for their domains. And that's wonderful, because what happens here is I work a lot with medical science. And in medical science, I sometimes need to work with diseases. And I don't want to be creating my own ontology about diseases because I'm not an epidemiologist, I'm not a medical doctor. So I want to use the expertise of who are the experts on that area to leverage their terms, to leverage their knowledge in my work. So I go there, and for instance, there's an ontology called Zoid that's just about diseases. If you talk about phenotypes, you can use an ontology called HP. If you want to use, there's so many ontologies in the medical field. And the problem now is the next problem, that is how you use them all. How I leverage not one ontology, but how I leverage many ontologies. And how I manage to use many ontologies to do something useful to me. Okay? Then that comes the next problem that we have, that is the following. Ontologies, they just talk about concepts. They just talk about what we call intentions. It's pretty much like if you have a database, a relational database, it's just like having a schema for the database. But if you have a schema of the database, you do not have really content about anything. You cannot say that you have a company that has departments that have employees. That's what a schema is telling you. But you don't know how many departments, you don't know the name of the departments, you don't know who works within each department. This is the real content, the data that feeds into that schema, right? So just think now in terms of web and think in terms of ontology. We have been developing the schema, but we do not have the database, right? We know that we have a company that has departments and have people, but we don't know who are the people, what are the departments, what's the relationship of how many people work in department X, if it's not a matricial system where you have a person working for many departments and so on and so forth. So what is the solution for this? The solution for this is not to stick just to the ontology, but go to the next level, that is to work with what we call knowledge graph. Knowledge graph is something that is catching up like fire. We had a conference that started 2 years ago with 50 people. Second year, we have 1,000 people. Last year, we have almost 3,000 people. And probably next year is going to have, I don't know, 10,000 people. It's growing a lot. There is where most of the action is in this knowledge field, especially related to the semantic web. Having said all of this big picture, I'm going to go back to and I will leave this here in another screen and going back to the original presentation here, if I can find it. Okay, where is that? Here. Okay, so here is what we see. We see that we have been, now let me step back a little bit for a moment regarding the ontologies and knowledge graph, and we're going to get back there. But let's talk about data. Data has had a boom during the last 10 years, and I think it's the main reason why, for instance, I have been in the artificial intelligence field for almost 20 years. And 20 years ago, if you are saying, when I was there at Stanford, for instance, the database group was king. If you're in the database group, you are the best. If we're working with artificial intelligence at that time, believe it or not, the sense was, oh, you work in a really cool area, but you have not done anything useful in your life. Okay, this was artificial intelligence 20 years ago. And things have changed a little bit since then. I have been participant of the AAAI and each KAI conference that are the two top conferences in artificial intelligence during 20 years. Most of my time there, I had not got the attention of a lot of people outside of the community. And this has changed drastically during the last 10 years. So drastically that today I don't know who does not know what artificial intelligence is. And everybody's an expert in the field suddenly. That's fine. That everybody is an expert there. But I strongly claim that all this fame and prestige that we have today with artificial intelligence is just because we have data. Okay? It all started with a subfield of artificial intelligence called machine learning. That many times you're not doing anything more than applying statistics that have been around for forever to get cool results out of the data that you already have. Right? Okay, so the whole point here is that we have had data for such a long time. And probably the best thing to mention about artificial intelligence and data is to talk about something called ChatGPT. Right? Who does not know what ChatGPT is, right? What is the problem with ChatGPT? The problem with ChatGPT is that it's just a model that we are building on relevance of terms. ChatGPT, surprisingly enough, create amazing things without any level of reasoning. It has no reasoning, it has no capacity of doing more complex tasks other than find the next term giving a context. And on doing that, it has proved that it changed the world. Now, they are saying that the major breakthrough in artificial intelligence, especially in this area of large language model, has reached a limit on what they can do. But the reality is that it has not. I'm a big fan of ChatGPT. I use it for a lot of things. It has affected my area specifically a lot because one of the best things that what ChatGPT can do is to write code. Okay, but the point is that you need to have knowledge to cross-check what has been done with many techniques, not only ChatGPT. So if you want to increase the quality of your response, you need to get a response from ChatGPT or for any tool that does something like ChatGPT, any generative AI that you use, you can go there and plug to it something that could verify the result and see if it's correct or not. And if it's not correct, by just asking the very same ChatGPT to review what it has done, the precision of the accuracy of what you can get increases drastically. Okay, it increases from 40% to almost 9% right away just by asking ChatGPT to recompute your answer, knowing that the answer you have is not satisfactory to you. Okay, so knowing that what you're getting is correct or not is key for the evolution of artificial intelligence and any question answering system that you may have. Now, how you can get something that can go there and figure out if an answer is correct or not? That's a key point. One way of doing it is to build knowledge graphs. and to make queries on top of knowledge graph and cross-reference that with the result you have from something like ChatGPT. That's the future. That is really the future. So, for instance, if you go there and see a talk by Gary Nagu from Stanford, that's basically the guru behind all this ChatGPT and LLM models. He talks about making this AI approach agentic, making it with agents. What are the agents that he's talking about? He's talking about one agent, for instance, being LLM, and another agent being something that can talk to LLM and say, you give me a right answer, you give me a wrong answer, right? So, okay, I don't know if you see where I'm going, but I'm saying that the future is not only ChatGPT. It's ChatGPT plus, it's LLMs, and not only LLMs, all the new AI stuff, plus knowledge graph. And this plus knowledge graph is you being able to do it in a way that you're preserving the truth, at least at the knowledge graph level. Because in the AI approach, if you're only ingesting data and not making any decision of the quality of the data you are doing it, eventually somebody will need to do it. And that somebody may be the person building the knowledge graph. Right? Now, what is the key thing for you to build a knowledge graph that is high quality? Is for you to have high quality ontologies. Okay, if you have high quality ontologies and you populate them properly, you build high quality knowledge graphs. If you build high quality knowledge graphs and you cross-reference with any data analysis you do, you're going to have high quality results with high level of scalability. And that's the big picture of artificial intelligence, probably for the next 10 years. If you are following everything I said, you may be thinking, okay, I really need to love knowledge graphs. That's the whole point I'm talking up to this point in this talk. If you're building high quality knowledge graphs, you are in a wonderful situation to make difference on everything that is required, for instance, data analysis. So now I'm going to really dive into the talk and go more straightforward on top of the topics I have here. It's going to be a little bit technical. And I would ask everybody here who is in the room or even through Zoom, if you have a question, please stop me and ask the question, because I think it's more important for you to understand than for me to just go through this content, you do not get it. Okay? And I'm very happy to answer. So I think one of the problems I mentioned here is that we need to have ontologies to guide the process of building knowledge graph. And we are going to do it because we want to improve the quality of machine learning. And not on machine learning, to improve the process of any data analysis you are doing. And the problem we have for that, so this is the picture here. You need to acquire data. You need to do this bad thing called data preparation, and then you do the analytics. Why I'm saying that data preparation is a bad thing? It's a bad thing because it's very boring to do it. It's very annoying. And more than that, it takes 60 to 80% of all the time you spend doing data analytics. So most people doing data science, they spend a lot of their life doing data preparation more than data analytics. And if you have a way of organizing your knowledge and being able to do data preparation in a more systematic way, you have basically broken the most important bottleneck you have to have quality data that would enable AI. That is kind of the big picture. Any question here regarding this picture here? Is this crystal clear? Okay, when I mean data analytics here, basically I mean everything that we have seen with AI during the last 10 years, including LLM. Now, I have developed an infrastructure for managing knowledge graphs and to build and manage knowledge within a knowledge graph. This thing is called the Human Aware Science Ontology Repository. That is called Haskell Repo. And I need to stop this. Sorry. And I'm emphasizing the Haskell because Haskell is an ontology that we published something like in 2018. How many years already? 6 years.
Is it based on the RDFS or all?
It's RDF.
It's
It's all. It has all. That's all.
all.
All. Okay. So you see the picture here. Okay, what the thing so okay. So we have one of the things I decided during the last. This is not as critical as it appears to be. The semantic part here that is really those two boxes on the left. This is the knowledge graph or the graph database. Right now I'm using Fuzeki for some specific reasons. Could be Allegro graph or could be any of the 20 graph database you have outside there, as long as they are compatible with RDF. So that's what I'm looking for. I'm looking for a database that's RDF based and I can perform Spark queries. And I have already played within this infrastructure with at least 4 or 5 of them, and most of them they are plug and play. You just go there and get them to work for you. Then I have an API level based on Java and Play framework that use Gina to write the queries here. And it has a security package called Pack4j. And this is the background of this repository. On the front end of this repository, we decided to use Drupal. Why we want to use Drupal? Many reasons. First, it's because it has all this support for users, creating permissions to have a whole framework for editing. So, for instance, you can go there and add the content there, and you can have a reviewer to go there and review the content and approve, and then you can have the content published just after approval. It's very easy to create a functionality and block it according to user roles. So there are a lot of little things you get for free by using Drupal. But one important thing is that Drupal is a content management system. And one of the things we want is to really upload, and that's a very important term in terms of the repository, upload content inside of it. Okay? So which kind of content I want to upload inside of the repository? I want to upload data files. I want to upload data streams like MQTT. And if it's an MQTT that does not have a document that you're uploading, you want, for instance, to get that content and feed into our database. The database I'm going to feed is not the database inside of the back of this repository here. Drupal has its own relational database. In this case, we are using MariaDB, or can be any, it could be Postgres, MySQL, whatever. And what happens is that we have developed a way that all the backend information goes through the API. And we have those modules here where you deal with the several elements that you have for each module. Why we have created those modules? Because we have many projects using our solution, each one of them with a different interest. So, for instance, we work with University of California, Los Angeles, and they work a lot with questionnaires. And we have this model called SIR, that is the Semantic Information Instrument Repository. And questionnaires are kind of an instrument. They do not really care a lot about the knowledge graph at this point. They care a lot about the questionnaires. So you can go there and just install SIR and forget about everything else. Here with Luleo, we work with the Arrowhead project, and they have use case. So a use case for us is a study. It's a kind of a study. We have formal studies within our. I'm actually going to spend most of the rest of this talk about a very large study done by CDC in the US. So we can handle formal studies and we can handle informal studies like a use case. Another thing that I saw yesterday many times in Oscar's talk, he was talking about configuration of equipment inside of an industrial plant. And we have all the support for that. We have a DPL module, that's the deployment module. That's where you say, okay, I have this instrument that has this detector capable of measuring these variables. And they are organized this way. In this part of the plant, I have those sensors deployed, and then I have all the details that you can imagine about deploying a sensor, for instance, the dependencies, the maintenance, the life cycle of the elements. And more than that, I have a connection of the data to the life cycle of the sensors that are involved in the process of collecting data. And that's something that very few solutions support. So it's really nice that you do not only have an ontology. I do not have a large ontology that do everything for me. I have many ontologies around that I put together. And the same way, the repository works in a way that you can select which part of it you want to use. You don't need to use everything, and we don't need to have every single user using every single facility we have. Especially because this can be overwhelming. This whole back end and front end, we have more than 120,000 lines of code right now. And it's more than 10 years of development, and it has already costed NIH something like $5 million to develop. It's all open source. You can go there, get it, install it here at Luleo or wherever you are. And in the past, it used to be very difficult to install it because you need to install many components here. You need to do all the configuration. But right now, this is something that has happened during the last 6 months. We have streamlined the process of deploying everything. We already have been using Docker for many years, but we have improved the Docker configuration so that it's almost you clicking one button and installing everything. Actually, I did it yesterday when we were having a discussion with John, and it did work. I was happy to see that work. And our goal is to already deploy this tool for the first time already with an exemplary study inside of it. And we have a documentation that we have put together that's saying get started with this infrastructure. By just going there and playing with this study that's given, you can get a running version of this repository with a study that you can fully go there, not only upload, but ingest the content. I'm going to be talking about what is ingestion because that is really the meat of what I'm presenting here today. Okay, so going to the next point I would like to make is that data repositories, we have plenty out there. There are hundreds, if not thousands, of data repository systems available there. The question I have is how many of them are based on knowledge graph?
Yeah, it jumped back.
Okay. There's a delay. Oh, it's showing one thing here, another thing there.
Just lagging.
Okay.
Okay. All right. So if you think about data lakes, that's something that many corporations are doing these days. They get a hold of every single data file, every single spreadsheet they have, every single database they have, and they dump it all in a single place. So, right, you have all the data you have. But the big question I have is, how about the metadata? How about the documentation of that study? You have a study and you have a rationale for having the instruments that you have selected for a study. Where is this rationale? Maybe in a publication that the authors of the study have done, maybe in a piece of documentation that is hidden someplace in the web, not that they are trying to hide it from you, but it's basically because it's too much information to show and it's really hard for you to emphasize what's important or not for certain user. So basically what happens is that you may have a lot of data, you may have a lot of metadata, but in real life, in most of the cases, they are completely disconnected and you cannot use both of them together, period. Okay? Now, what we want to do here is to have not only the data inside of a RDF model that is our semantic model, right? But we also want to have the data's metadata inside of it. And more than that, we want to be able to query all of this content in a systematic way. So this is the meat of our data repository, is the capability of having data and metadata together inside of semantic model and to be able to query it. So, just naming things, this is just kind of a lecture slide. The ontology define classes. The classes can have instances. These instances may have properties, and these properties may have values. Okay? This is what RDF does. And this is what you see inside of our repository, because it has all the ontologies that you need inside of them. It has all the instances, and these instances I like to emphasize it because many times people do not completely ignore them. And I will show you how instances are ignored in a little bit. And then what is also important to mention here is that not only that we have all of these pieces together, classes, instances, properties, and values, but we have them and they are interconnected. Because this interconnection is the knowledge that we are dropping all the time during our lifetime, and we completely ignore it. Who here has never done a spreadsheet? When you write a spreadsheet, just by writing it, you are dropping knowledge. There are so many things you know about the knowledge that you're putting in the spreadsheet that does not go inside of the spreadsheet. And that is the tragic part of how technology works, is that we are doing kind of a bad job preserving our knowledge, and we are not even aware that we are doing it. And it's not only me, you, it's everybody. And it's everybody doing it forever. Right? So, and people struggle with this. How many people get a spreadsheet and then need to call the person who created the spreadsheet and ask for clarification? That thing of sharing information is very essential. Documentation is not necessarily just for you documenting your stuff for yourself. It's you creating documentation that a person who is not you is going to benefit from that documentation. That third-party person involved in the process of sharing knowledge and information is the big challenge. Because that third-party person does not know how to understand your data. And sometimes, if you really pay attention to this, and you can write the documentation. Just go to your own laptop if you already have it for a few years, or if you have. Go to a spreadsheet you have created 5, 10 years ago and try to understand it. And I'm talking about you talking to yourself, right? This is the challenge we have here. And what we want to do is to preserve all of this. Now, here, I would like to make an important point of how this whole thing works. Because the first thing is to move the content into the repository. So I need to have the data files, the raw data sets. If I have an MQTT, I need to have the dump of the message in some place. This is just bringing the content inside of the repository. Bringing them inside of the repository, that's what I mean by upload. It's not solving my problems. It's not building any knowledge graph. It's just bringing the content close. Okay? The real and complex challenge here is to do phase 2 and phase 3. That is ingest the content. Ingest the content means for me opening the data files, opening the documentation, understand what's there, and bring it together into the graph database in RDF, and all built in a logical way. So you're going to say, this is challenge. How am I in terms of time here?
Yeah, for the presentation, yes.
I'm already over.
No, 8 more minutes.
8 more minutes. Okay, I really want to make a point here in terms of what is the key piece that that you may want to pay attention. So I'm going to run a little bit. I have something called a metadata template. Metadata template is a strategy we have to encode metadata so that we know how to ingest it. And we have a number of those for different purposes. I have a metadata template for study content, for instrument specification, for deployment specification, for streaming specification, and one that's really, really key is the semantic data dictionary. Data dictionaries are things that have been around for many, many years. If you work in a relational database, even Oracle or IBM old data management systems, they would have a data dictionary page. You go there. Every single table have properties and rows, and you could go there and document what's the meaning of each row. That's a data dictionary. Now, here in this is the slide, if you walk away understanding a little bit more about this thing, we are in a good shape. So the first thing you see there on the top, you have 4 green areas there, right? So four documents. You have the raw data that's on the top left. Then you have the documentation that is, in this case, is a data dictionary. Then you have the ontologies that we talk about a lot at the beginning. That is the one on the bottom right. And eventually we have the thing on the top right. That is the meat of everything. And what you see there is that the document on the top, the semantic data dictionary, is the big glue of everything. It has the column headers of the data sets. So, for instance, you have there the read age, year, read the year. I don't know how to say that. That's a column header on the data set. In the first row, you see 2. Okay. If you go to the document on the bottom, that's going to say, hey, that is age in years. And then you have, at the time of the screening interview, is reported for survey participated between the age of 1 and 79. All respondent participants aged 80 years and older, or just call it 80, and so on and so forth. So that has a specific meaning of that number 2, that number 66, that number 18 you see on the top. It's not any age. And for instance, remember those things we talk about, the machine does not understand what we are talking about. So that text that you see there is for human consumption. You see the age in years. What that thing means for a computer. What is year for a computer? Right? I don't know. Now, if you go there on the right, you're going to see a definition of year that's in English as well, but you have an identifier. And if you go inside of that identifier, that is a subclass of time interval. Just because it's time interval, I know that is a period of time, and I know that has a bunch of properties, like you have things that come before, you have things that come after, they may have a duration, and so on and so forth. And then I can go there and compare that to seconds, to minutes, to a lot of other units. And this capability of understanding what a year means is what makes that concept useful for a computer. Because if you have things that are not in year, the computer knows this is not in an age in year. And if it's in seconds and you know how to convert it, because the conversion is also inside of the ontology, you can convert that to any other unit you have of time. That's the beauty of bringing semantics to the content that you are ingesting. Now, if you go to the thing on the top right, that is the semantic data dictionary. That is the thing that we are building for every single study that we ingest inside of Haskell Ripple. It's actually the bottleneck for it. We have Mark Johnson, that guy from the Air Force, that is working with us. He finished his PhD and he used machine learning to generate the semantic data dictionary from text, from documentation, and also going and building something like a large language model just for populating semantic data dictionaries. Is his work done? No. There are a lot of opportunities of research on top of semantic data dictionaries. Why I think semantic data dictionaries are key. Here in Europe, and you were talking about, Oscar was talking about this yesterday, we have this DPP, right? Digital Product Passport. So the Digital Product Passport is a description of the product. But if the product is something that generates data, what I really want from it is to have the SDD, the Semantic Data Dictionary, of that product. What is the benefit of doing that? Well, if the maker of the product provides an SDD specifying the semantics of the data that's generated, then we're removing the bottleneck of understanding the data for every data collected from that instrument. This can be a revolution on us of streamlining the understanding of data. That's the key for interoperability, because I may have another data set that is based on a different semantic data dictionary, but it's a lot easier for us to talk about how two SDDs are different than to talk about how two data dictionaries or even two data sets are different. In the arrowhead, we have consumers and producers. They are sharing data, but I do not know the meaning of what they are sharing. If you are sharing information that we know what is the SDD of everything you're sharing, we can at least have a good shot of trying to solve the problem at the machine level. If you do not have SDDs or anything similar to it, I'm not saying that's the only solution. I'm biased here because I'm one of the developers of the SDD, and this is the thing we're selling. But I haven't seen other approach to do it as sophisticated as ours and with the level of impact we have already had. So SDD is part of the solution for us to build knowledge graphs. Why? Because SDDs, the knowledge graph is important because it does not only have the ontologies and the instances, but it has the values. And putting the values inside of the knowledge graph is one of the key challenges we have, right? Now, I'm going to skip all of this because then I start talking about instrumentation, data acquisition, which kind of instruments we have, which kind of studies we have, which kind of object collections we have. And I could even mention this large repository we have in the United States that is used by 200 universities, almost 500 scientists. That is the HERE project. Just to give you a final view of what's going on here, we have something like 200 studies dealing with a number of diseases like asthma, like autism, like cancer, all related to environmental science, environmental health science. That's a huge project. The funding for this is in the order of billions of dollars, literally. And you have at that time we had only 31 studies and 1,200 variables already. These days, I think it's more than 100 studies we already have there. So the beauty of this is that you can, okay, another delay there. Okay, the beauty here is that,
We just have to wait. It's lagging. So
May I ask question?
oh yes,
So, am I understand correctly that you somehow create a kind of new global knowledge base? But there are many previous attempts on that on ontologies knowledge base, like famous psych of Duke Leonard, yes?
yeah, no side.
And so you mentioned interoperability, and is it what is the way to integrate all those previous ontologies to your system so that creating those semantic dictionaries? So there is some straightforward way to integrate all
Okay.
available knowledge before your project.
Psych does not have the structure for handling studies. It's a plain knowledge graph. This guy here, one of the co-authors of this study, is one of the key developers of Psych with Doug Leonard. Jim Masters here. He worked for Psych for 10 years. He could even explain you a lot more about how comparing something like Psych. Psych is a knowledge, it's not a knowledge graph, full-fledged, okay? And it has something called the microtheorems. Do you know a little bit more Psych? So the microtheorem is not a common understanding like RDF, and you cannot do any trust maintenance system on top of Psych. So in other words, you could not conciliate all the knowledge inside of Psych. So that's why when you're using Psych, you need to define preferences, and then you start slicing it. So but he was dealing with a project that was working with. It has a different purpose. He's not analyzing he's not doing any data analytics on top, and he didn't have data inside of Psych. Psych is just at the schema level. It's not a knowledge graph, not a full-fledged knowledge graph.
But I mean, okay, this question can be extended to other knowledge graphs created within semantic web. I mean, there are plenty of full-fledged semantic graphs, like take Wiki, DB data, what is it?
DBP
data.
Yeah.
Okay, the problem of
Wiki
DBP,
data,
okay,
yeah, DB data.
they're wonderful as well. Okay, and I actually work with I did contributions to DBP, and we worked in 2 DARPA projects. I had a whole replica of DBP in my computer. The problem that you see there is that they do not have what I call the archetype. Okay, and because not having that, you basically could not do most of the useful queries. So for instance, just to give an example, you can go there and say something like, give me a list of all the locations you have in the planet, right? It would not know what to do. You need to be more specific and say, give me all the instances you have of cities, of states.
Okay, but
Now, if you want to go there and say, give me all the locations, all the things that can be locations, that becomes such a large query and so useless because it's so comprehensive.
yeah, so the question is, can we somehow use anyway those previous knowledge? Maybe it is not so well organized, etc. But is it now useless at all?
No, they're not useless at all. We should be doing combination. I'm not completely. I actually use a lot of Wikipedia. So how I work here is the following way. If I'm working with a concept that I don't want to spend a lot of time working with that concept because it's not really useful for my scientific purpose, I make a reference to the Wikipedia inside of my knowledge graph, saying this is the Q term because everything that is a Q, whatever, and this is the reference for it. I think the main difference is the following. And that's a conversation I was having with John yesterday. It's like an ontology. Okay, that's a good answer for you. When you develop an ontology, and that was a major problem we had during 10 years, we would go there and start talking with people in earth science and say, oh, we have RDF, we have Protégé to go there and edit. And they would start paying attention to us, especially when their colleagues start working that field. Once they learn how to go there and start to write their own ontologies, they get so addicted to it, and they would spend days working on building their ontology. Okay? That's the problem. Because what we do, and if you go to Deborah McGinnis, the Ontology Development 101, she says, you can go there and build the ontology you want, but the right way of building ontologies that are useful for you is to have a purpose for that ontology. And you make a purpose of that ontology, developing use cases, making a requirement engineering on top of the use cases. And then you break down that into competency questions. So you are working a scientific study, you have the questions you want to answer, right? So if you want to answer those questions, you need to have, those are your competence questions. They're not RDF questions. The first thing is to figure out how you're going to break down your competence questions into RDF. Once you have known that, then you're going to start figuring out what are the missing pieces you have.
Yeah, so you have a recipe for newcomers, so to say, people who begins to work in some area in proper way, so it could be used in your system, or otherwise he can use your system. But what is with the previous works, previous research, previous ontologies? Can they be somehow adapted to your framework?
Okay, but that's the answer I want to give to you. And go back to the exact two topics I mentioned. What is the goal of Psych? Goal of Psych was to participate on the 5th generation challenge that was developed in '89. That's why the government funded Psych to build a model to compete with Japan in the 5th generation project. And that's why Doug Leonard got that funding, and I actually worked for 2 years collaborating with him in 2 co-projects. Their goal was to have knowledge about everything. Their goal was to have all the knowledge that 3-year-old would have, because their belief was, if you build an agent capable of getting all the knowledge of a 3-year-old, then this agent will be able to learn from itself and evolve like a human being. That was the Psych proposal, was a knowledge about everything, no purpose, right? DBpedia, they have a purpose. Do you know what's the purpose? To have a replica of the whole Wikipedia in a graph. That's not the purpose for having a competence question, right? I'm working a scientific project where I'm dealing with scientists who are dealing with real life problems. Those are the people who figure out that you cannot have door with asbestos. They do not. You cannot paint a wall with lead. This is the science. You cannot have a toy with phthalates, and we have a list of 5.8 million chemical elements that we are studying. And that's our goal, is to understand how the environment affects us humans. It's not just collecting knowledge. We have a purpose. That's why we have been working with 58 ontologists, bringing together to fulfill the mission of those 100 studies we have selected from 200 universities and to answer specific questions. If I was just going to build Psych or DBpedia, I would not evolve environmental health science, right?
No, but
Pedro,
I mean, okay, so
may,
that's
may I ask a question?
Yes.
Since you are touching upon this integration problem, you're having a large problem. Take the environmental point you're making there, which apparently will need, I guess, a number of ontologies. And with further understanding of the environment, there will be yet another ontologies to be considered, or data that need yet another ontology. And this is not a kind of a static environment. This is a development with languages, with understanding, and with culture, and all these kind of things. But it brings us to a situation: how do we integrate ontologies? How do we create the understanding between ontologies, or with the integration of ontologies, and can we automate this process in one way or another?
Okay, so first part is how we integrate things, how we integrate ontologies. That is, okay, even before of that, all the knowledge we have it's not non-monotonic. Okay, we can retract knowledge. We are able to maintain truth by seeing which kind of derivations have been done. We can persist reasoning inside of the knowledge graph, and we can retract knowledge as well. Now, what I see that's also a big mistake is that people take things face value and they start importing ontologies inside of each other. And that's not a good thing. There is one approach called myriad. Have you heard about it? Myriad is the way of you selecting from existing ontology which parts of it are relevant for you. And you can do a sanity checking with using of consistency checking to see if the myriad part of a given ontology affects the existing knowledge base you have. Now, if you pick an ontology that the whole ontology is relevant for you, then you can fully import it inside of your knowledge graph. So it's not one full integration of everything with everything else. That I do not believe. And that creates a lot of mess in your environment, because if you bring a large ontology, Jan and Oscar will talk about bringing CABI inside of their study. Okay, if you're bringing CAB because you are importing 3 or 4 concepts, import 3 or 4 concepts. If you need to leverage a little bit of the hierarchy and my upper level classes and probably some downstream classes, you import just that piece. Yeah. Because CAB itself is something so large and so complex that if you just import that inside of Protégé, you cannot even open it. I'm really sorry. So I think I answered most of your questions.
to my understanding, one of important questions of Yerker, and which is I believe is one of unresolved questions in this domain, is automatic aspect. How you can automatically merge select ontologies, because that was one of the main reasons for failure of semantic web as a technology. As a global technology.
Right. So the thing I was just mentioning about math that is capable of building semantic data dictionaries automatically, that is in the way we believe we can start addressing the problems of how systematically overcome the main bottlenecks we have in the process of building knowledge graphs. Okay. It's work in progress. I do not have something that's really, really useful. It has proved to be useful in many scenarios. But yes, it has potential to reach the point where we believe that 3-5 years we will be able to get that thing done automatically. And that is basically exactly the same thing of bringing integrated ontology. Now, Jagger, regarding your question there, I think the one of the key problems is exactly what I was talking about, the digital product passports. If they do have data dictionaries, semantic data dictionaries attached to them, you are a lot better to support things inside of Arrowhead, especially interoperability, and especially if you talk about the orchestration of services. Because if you really know what are the variables and what are the semantics describing all the dimensions of variables, and then you should be able to better coordinate the services that are registered inside of Arrowhead.
I totally agree on that. But it's back to
right.
But let me comment on that since. But the bottleneck in actually doing this is actually the engineering part of it, and that is why my question on the automation part, since automating there's annotation of metadata to any data, and that is part of the semantic the SPP, so to say, and people don't understand this. They've never done it, and this is where the big bottleneck to actually bring this to life.
I think a big part of the solution of this problem, Jürgen, is basically the DPP. Because what happens is that if you just go, for instance, to any of our partners, they have tens, hundreds, thousands of sensors. And if they have thousands of sensors, they have data sets with thousands of columns. Now, if you are using these thousands of columns of data, and you are the one creating the semantic dictionary for all of that, you are spending all your time just doing semantic data dictionary. On the other hand,
yes, and some companies do start on this journey, but it's super expensive. And this is why I'm putting the automation question there. But I think we are very much on the same page.
Right.
We identify where the problems are, and this is, I think, is the very important point about your talk today. That at least I can see that we are the arguments ends up in certain things which need to be addressed further, which of course will be subjects for future research projects and collaboration projects. And this is what I appreciate with your talk today.
Okay, thank you for your appreciation. And I'm glad you're asking those questions too. This is something we have been meeting for so long and not asking those questions. But going back to the solution I see, the solution I see is partially improving this work that we already started doing it. But the other part is, if when you buy a sensor, the sensor comes with a semantic data dictionary, and you have a process of leveraging and taking advantage of that semantic data dictionary, then you may not need to do any semantic data dictionary. because if you're using 1,000 sensors of 1,000 different kinds of sensors, and if all of them come with their own data dictionary, semantic data dictionary, then you don't need to do anything. You just need to leverage this semantic data dictionary. Now, the problem that I see, especially with this project that we are doing with Mount Sinai in New York, is that we receive data from 200 scientists. Each scientist has something like 100, 200, 300 variables. And we have this group at Columbia University that's Jeanette Stingone. I'm sorry for her, but she loves to do it. She's an epidemiologist. She has a whole group within Columbia University just learning how to do dictionary for epidemiology. And it's time consuming, and you need to be very careful because if you put the wrong context there, you affect everything downstream in terms of the quality of the data. It doesn't matter if you have a good ontology. If you build a bad, you can easily build a bad knowledge graph on a very good collection of ontologies. And so the solution is threefold. One is to improve ways of automating it with more artificial intelligence. That's part one. Part two, I would say, is to have an infrastructure that can take advantage of this knowledge if this knowledge is presented to you when you buy the instrument or the detector, right? And the third thing is actually for the makers of those things to provide you the semantic data dictionaries together with the product. Because if they provide to you, do not use, you're not benefiting from it. But if you buy the instrument and does not come with it, it's up to you to do it. And that's what's going on these days. And I would say even more, I do not believe in silver bullet here. What I mean is this: if you really want to have semantic understanding of your data, you do need to do something like our semantic data dictionary or something else. And this something else is not going to be any easier than what we are doing. That's my point. Just take any variable. We have been talking about the room temperature example that I started doing it, then John tapped on top of it, and you present there in Belgium. Okay, room temperature is one thing. The other thing is to have room temperature at time X, at location Y, okay, playing a role of being dry bulb or wet bulb room temperature, because it may be indoor, may be outdoor. When you start putting all the context around any scientific variable you have, you start seeing how complex that variable is. And that's exactly why I am not afraid of competition. Because we have been working with this thing for 15 years, and it's very easy for me to see that you can break this if you do not have all the experience and I would say baggage to build this thing together. And for instance, the other thing that is very, very easy to see how you can break this whole solution here is not taking care of life cycle. So I see some of our collaborators developing ontologies and knowledge graph, but they do not assume that once you have the sensor in place, that sensor may not be functional next week, that you need to go there, remove it, and put another sensor in place. Or even worse, if you have a scientific instrument, you need to systematically and with some regularity remove it to do calibration, to see if the thing is still working as it's supposed to be. And more than that, depending on the area you are, when you do the calibration, you generate calibration data that needs to be applied for all the data measured after that. That for me is crystal clear. I was just mentioning this to John yesterday. I work in the same group that created GPS at National Center for Atmospheric Research. And every astronomical image, you need to take a picture of the room where you are, because the temperature of the room works as a lens that affect the quality of the image. And then every single image you take with that telescope from now on, you need to go and you need to apply the lens to cancel the effect of the atmosphere within the room that took the picture. That's a common example. I have seen that also working for Woods Hole, that is the organization that do the mapping of the Atlantic and Pacific Ocean for the US government. They have many examples of deployments with life cycle. So you prepare a whole ship for a mission of 3 months. When the ship goes back, you disassemble everything and you assemble everything for the next mission. That may be other instruments with other configuration, with other settings. Are we really prepared to work in such a dynamic environment? Because I see people, for instance, some of our partners talk about knowledge graph, where everything is static. You put them there and you do not change anything. That's not how life works. They need to take care about life cycle of deployments, of sensors being in a place, of sensors breaking down, of you doing maintenance of the sensors, and more than that, if the sensor is collecting data as it's supposed to be, you need to be able to track that back. So when I was working for the Department of Energy, we worked in the ARM project that was collecting the most important data set for climate change. And you will be surprised how important it is to track who is using your data. Not because you want to know the impact of it, but because if you use that data and 3 years from now somebody discovers that there is some quality issue in your data, they can call you back and say, hey, that data set you got from us may not be as good as we thought it was. That's how ARM works. And they have sensors deployed all over the world. And they have 50 years of data, and they have more than 5,000 scientists using their data on a daily basis. That is the level of control of the data that we have in this infrastructure I'm presenting to you now.
So Yerker wrote in the chat that he needed to leave.
I think we will end the session now. We see that this is a hot topic with interest, and it will affect us for quite some time. So the discussion ends for the seminar, not for us.
Right.
We continue after.
All right, but let's thank.
Yeah.
Thank you very much.
Thank you very much.
Thank you.
Actually,